So good morning and welcome back. So today we finally complete our discussion of Lie groups. And so what we did so far, we start with the Lie group G, and we studied the corresponding Lie algebra as first the set of all the left invariant vector fields. And so because coming from a group to the vector fields, we invoked some differentiation of sorts. And today we are going to answer the question of why these left invariant vector fields are so interesting if you want to study Lie groups. Well, you can derive them from there, but what do you learn about the group once you know the algebra? So today we'll be concerned with the question of how to go back up there, and I can already anticipate the result. At least in a neighborhood of the identity. Up here there's an identity element. At least in a neighborhood of the identity, you can fully recover every Lie group from its Lie algebra. How big this neighborhood is, that depends, and we'll look at that too. And this going up there again will be achieved by something that we'll call the exponential map. So we have section 4.7. Recovering, and let's be careful, some, maybe all, some of the Lie group from its Lie algebra. All right, so the first thing we're going to do, well, we know that down here we actually have this isomorphism to the tangent space at the identity, but now we will also on occasion have to invoke the left invariant vector fields again to understand this exponential map. Well, but the first thing I want to provide is a definition we could have brought much earlier. And that's the following. Let M be a smooth manifold, and let Y be a vector field, a smooth vector field on M. Then an integral curve, or then a smooth curve gamma, and now we've got to be a little careful with the parameter range. Let's say with a parameter range from some real number A to some real number B into the smooth manifold is called an integral curve. If for every point along the curve, that means if for any parameter value lambda in the interval AB, it is true that the tangent vector to the curve at the point gamma of lambda, remember we always indicated the tangent vector to a curve by this symbol x curve comma at the point. If this point is actually, if the tangent vector at the point is actually given by the given vector field at the very same point through which the curve passes. So that's an integral curve. Well, it's quite obvious that there is a unique integral curve through each point of the manifold, integral curve of a vector field y through each point of the manifold. Well, if I say it's obvious, well, actually this obvious follows from the local existence and uniqueness of solutions to ordinary differential equations. Okay, so the idea is you have a vector field on your manifold, and you go to an arbitrary point of the manifold, like say this one, where of course there sits a vector, and now you can find a curve whose tangent vectors coincide with the vectors that are already given. And locally around a point, if the vector field is smooth, that's important, so it needs to be a smooth vector field obviously, then this is unique. Okay, so now that's this. Now there's an important definition which at first sight seems a little, well, not so important, but it is. Also plays a big role in the singularity theorems in general relativity, but let's have this first like this. A curve gamma, an integral curve gamma of a vector field y is called complete if its domain, so that's what I called the parameter range before, if its domain can be extended to all of R, so AB, well, to all of R. It's complete. So there is a result that says that on a compact manifold, every vector field is complete. So we always talk about smooth vector fields. Every smooth vector field, every vector field is complete. Now, and only on a non-compact manifold, this is not necessarily the case. Now, let's look at an example to immediately withstand the temptation to look not closely enough. So imagine you have a sphere. Okay, let's take the sphere, surface of the sphere, it's an S2, and we look at a smooth vector field. Well, we already know we cannot comb the sphere, so that means we might, if we want to have a vector field here, we know at some point it must vanish, okay? And if it's a smooth vector field, briefly before that, it needs to be small, and then if you, as you go away, you can maybe make it bigger, right? But we know there must be such a point where it vanishes. We use this argument, you cannot comb a sphere, when we discussed the non-existence of bases of the module of vector fields and so on. So let's say we're on the sphere and it looks like this. Now, the sphere is compact, but here it really looks like, at first sight, that, and that's actually true, say you go through this point and you find the integral curve goes here, and of course it stops at this point, because if you went on, you can no longer run in the same direction, right? Because then the tangent vector would be opposite to the field. So this curve stops here, whatever it does over here. So it seems like it cannot be complete. Why is it complete? Well, because we're not talking about the image of the curve, we're talking about the parameter. And indeed, in order to arrive at that point, I need to go to infinite parameter, because the vectors of the y field, they get shorter and shorter and shorter and shorter and shorter. So the curve must become slower and slower and slower, such that the tangent curves really coincide with the vectors that become shorter and shorter. And indeed, you only arrive here at infinite parameter value. Or you could also say you never arrive there. Okay? So you cannot simply look at the image of a curve at this point set here and decide whether the curve is complete or not. Okay? And now if you have a non-compact manifold, you can have such situations that you have a curve and you come to a point, and so there's a vector field on there, and you come to a point and for a finite parameter b, and you cannot continue, or it's no longer an integral curve. Okay, so this is the completeness, and this is for general smooth manifolds M. I introduce this because for the special case of a smooth manifold G that is a Lie group, it turns out every left invariant vector field is complete, even if the manifold on which it lives, the group, is non-compact. That's the strong result. Okay, so theorem. Every left invariant vector field on a Lie group, which is a smooth manifold in particular, is complete. So that's a theorem one can prove. It's not so difficult to prove it, but it's a little lengthy. But it's a key result of Lie theory. It's one of the most important results, although it appears so innocent here. And the reason why it's so important is the following construction. Definition. Let's say we take an element from the tangent space at the identity. So what we decided would be the convenient space where we, in which we think the elements of the Lie algebra lie. Okay, let's take this and define the thus uniquely defined or uniquely determined left invariant vector field how shall we call this, x a, well, where, how was xa defined? Xa was defined such that at the point G of the manifold, it was given by the push forward of the left translations acting on the element A that lives at in the tangent space at the identity. This way we made from a single vector in the tangent space an entire left invariant vector field on the whole Lie group. Okay, let's say we do this. So we start with such an element. Then let gamma, which we also call gamma A, let gamma A from R to G, and this is now the point where we use the completeness, R to G, be the integral curve of this left invariant vector field through the point gamma of 0 being the identity, so I called it E over here, being the identity of the group. Okay, it lands in the group, so I can say at parameter value 0, I want to be at the identity, And how do I go on from there? Well, it depends in which direction my A points, and then I just follow an integral curve of this vector, left invariant vector field through that point. So and E, so I should write an A here. So it's clear this is uniquely defined. So I start with an A in the tangent space, and I get a particular curve through the identity following this A. So the derivative at the identity would be exactly this A, the tangent vector. Okay, to this point. This induces or defines, this curve defines, and here that I can define this for every parameter value. That is, of course, building on this theorem that the vector field is complete. So this defines the so-called exponential map And what does the exponential map do? Well, it has a pretty name. It's called exp. And it takes any element from the tangent space to the identity and maps it into the Lie algebra. So this is this path we wanted to go from the Lie algebra up to the Lie group. And it's defined as follows. It says that exp of sum A that I take from here is defined as exactly this integral curve gamma A evaluated at parameter value 1. So at parameter value 0, I'm at the identity, and now evaluated at parameter value 1. Now you say, why 1? Well, I could, of course, write here a lambda in front, and then I can have a lambda here because I can scale these guys. Okay, so it suffices to define this at 1, so-called exponential map. That's it. Okay. So remarks, or well, it's rather, let's call it a theorem because it is. So a theorem comes in several parts. The first part is that exp is a local diffeomorphism. A local diffeomorphism. So what does that mean? It means there exists a neighborhood so there exists I should say, well, it's a neighborhood of 0, of the 0 vector in this tangent space. It doesn't need to be a vector subspace. Well, it won't, of course. It's just a subset in a neighborhood of the 0 vector there, such that if you consider the restriction of the exponential map, such that exp restricted to this subset, and therefore mapping from V to exp of V, which is then a subset of the group, is A, bijective, and B, exp restricted to V and exp restricted to V inverse are both smooth. So that's a local diffeomorphism. So that means by knowing the Lie algebra, we understand the neighborhood of the identity of the group. Some neighborhood. Could be a large neighborhood. Second, if the Lie group G is compact, then exp is surjective. That means that exp indeed, you can start with the entire Lie algebra, and it will reproduce the entire group. That's nice. So for compact groups, understanding the Lie algebra, you get any group element back by exponentiating up. That's good. However, let's compare. So once one has such a result, something is surjective, you can start comparing the domain and the target. And we know that the domain is compact. Why? Well, that was our assumption here. And we can look at the target. And what do we know about the target? Is the target compact or non-compact? The domain, I'm sorry. It's a vector space. Is it compact or non-compact? Well, it's non-compact. Okay, it's not. This is non-compact. Now, if I have a map that's surjective, and it's of course a smooth map, we know that. Did I say that? So, well, the exponential map is smooth. Yeah, well, it's a smooth map. Well, if you have a smooth map that's bijective, then you would have established a diffeomorphism. But a diffeomorphism, in particular, is a homeomorphism, and it should send a compact space to a compact space, right? It should preserve this. So the point is, it cannot be injective, right? Because otherwise, it had to preserve the topological structure. Hence, it follows that exp, in this situation where G is compact, that means exp cannot be injective. So that means you can do this, you get the whole group, but you will hit elements twice, at least twice in here. Okay, so let me draw a little example. Let's say we take the S1, that's this nice circle here, and that's the smooth manifold underlying SO2. Well, if you talk about rotation, SO2, you need to give me an angle. So the underlying manifold is S1. So as a manifold, this is S1. And what's the tangent space at the identity? Well, let's say that's the identity, and that's the tangent space at the identity. This is T, so this is E. This is TE SO2. So the tangent space is the real line. That's not compact. This guy is compact. Now, if I exponentiate here, say I take this vector in the tangent space, and I take the x map of it, I land here. If I take double the vector, I take the x map of it, I land here. If I take a suitably long vector, I'm back here. If I take a vector that's even a little longer, I hit this point for the second time, and so on. And the same the other way around. So this is the example to this argument. Okay? Right.
Does part 2 of the theorem count for any mathematical function? Can I also use it for cosine or sine or anything like that?
You mean that if it's surjective,
Exactly, yeah.
and it maps you from a non-compact to a compact space? Well, if it's surjective, and of course it must be at least continuous in order to allow you to have a contradiction. Yeah, of course.
Okay.
Of course. Okay, so that's if G is compact. Now, if G is non-compact, it need not be surjective. So let me, well, that's a non-result. So nevertheless, let me state it as a non-result. So if G is non-compact, it may be not surjective, right? But it now could be injective because you no longer run into this trouble. Yeah? And it can be both. It may not be surjective, may be injective and may indeed be bijective. But you see, part 3 says nothing. Okay, it just warns you that nothing of what you concluded here applies there. Okay, and so an interesting non-compact group in physics is, of course, for instance, SO1, 3. The Lorentz group is non-compact. Choosing a basis A1 to A dim G of the tangent space at the identity, choosing a basis there, hence provides a, let's say, convenient, some emotional statement, provides a convenient parametrization of, or coordinatization, coordinatization of the Lie group. So, well, let's do something half physical. So let's say we take the tangent space to the identity of the Lorentz group. Then we can choose a basis that consists of m mu nus, like you usually call them. But every m mu nu is an element of TeSO13. And these mu nus, they run from 0 to 3, say. Okay. But so you have, and they're antisymmetric. So you have 6 of those. And that's right, because this is a 6-dimensional group. So the tangent space is 6-dimensional. So you can label the, these elements, these basis vectors, such. Okay. And, well, they have to satisfy a certain algebra. So you can ask what kind of algebra the m mu nus with the m rho sigmas satisfy. And if I remember correctly, that's some eta m plus eta m minus eta m minus eta m. And the only thing you got to do, and the eta is the Minkowski metric, and the only thing you need to do, you need to distribute the indices correctly here. And of course, you can calculate this from first principles. So I say this. So these are antisymmetric. So, well, you figure it out. Okay, so you look it up. So that's the Lorentz algebra, right? Is, or maybe our notation, we should write it somehow like this. Okay, it's the Lorentz algebra. And indeed, you get, well, you, hang on, do you get all of SO13? I think you just get the orthochronous subgroup, whatever. Anyway, you can consider X of any of these guys, but because they're a basis, I want to get any element of the tangent space here. Well, I can do this by providing linear combinations with coefficients, with 6 coefficients, which I label omega mu nu, but they're only 6 because this is just the label. So these omega mu nus, each of them is just a real number. And each of those guys is an element of the tangent space. And I can exponentiate those. And now I think, yeah, the only thing you get is you don't get back all SO13. I think you only get back SO13 and get, but please check this again. So you get SO13 only the orthochronous group, so where you don't have mirroring in the time direction. Where you always, okay, where you keep future pointing vectors future pointing. Okay, anyway, this is what we do in physics very often. We say these are the elements of the group, and this parameterizes the group. It's like coordinates on the group manifold, right? And they're very convenient coordinates, because if you look at them, because it's antisymmetric, you may, well, because it's a matrix, you can write this as a 4x4 matrix, but it's antisymmetric, so it has zeros on the diagonal. And if you look closely, then you have here psi 1, psi 2, psi 3, and here you have 1, 2, phi 3, 1, 3, minus phi 2, 3, 2, 2, 3, 1, phi 1, and then you have antisymmetric, this repeat on the other side, and these are the boost angles, the hyperbolic angles that tell you the boost in this and that direction with this and that total hyperbolic angle, and this is the rotation that's done at the same time. So this is a combined boost and rotation, and because you understand these guys, these parameters so well intuitively, right, as rotations and boosts, this is a very convenient coordinatization of this group. And in physics, you know that you very often think of the group as being generated, so that's terminology. You say these basis elements are the generators of the group, means nothing but they're a basis of the Lie algebra, and the group elements are generated this way by the exponential map. Now, this is the abstract version. If you now represent the algebra, that means you have a representation TE, well in this case SO13, and you decide to represent the algebra on, say, on R4, then each mu nu, so then you can say the rho, the representation of each basis element, you know the representation is linear, so I only need to define it on a basis, and the representation is then a matrix AB, right, where A and B run from 1 to 4, that acts on R4. And this is probably how you met these guys, and I think the this representation here is given by something like delta M. Okay, so how does that have to look like? No, delta M, of course. Delta eta, aha. Is delta eta, say, mu A nu B, and then there's again pluses and minuses of similar terms. Okay, and that's the vector representation. This is now just certain matrices. This is the vector representation there, and so on. Okay, so for instance, rho of M01, I think that's something like a boost in one direction that looks like this. Something of the type, and so on. Okay, so then you have a representation, and once you have a representation, you can plug the representation in here, and then this exp becomes just the exponential series applied to matrices, because they have an index up-down, because they're endomorphisms, they can be composed, and the power in the exponential series, where it says x to the n by n factorial, the power to the n is the power of the composition, one after the other, and then the exponential map becomes something very that coincides with the exponential map, you know, once you use a representation. But this here, as it's written here, is still fully in the abstract, and the exponential map is defined via the integral curves of the left invariant vector field generated from here. Okay, so that these are these different levels of abstraction on which you can discuss this, but after all, choosing a representation, it becomes very elementary, and that is why in physics we very often think of the groups and the algebras always in terms of some representation rather than abstractly. But in order to really get the background theorems on how you can use this and so on, we had to do what we did. Okay? So this is just to connect this to what you have seen in your physics lectures before. Okay. So we have another definition, very useful. And that's the definition of the one-dimensional subgroups, or as they're also called, the one-parameter subgroups. Okay, a one-parameter subgroup, this is just terminology, a one-parameter subgroup of a Lie group G is a Lie group homomorphism. That means a smooth map, let's call it Xi, a smooth map that goes from the Lie group R into the Lie group G. But in order to have R being a Lie group, I need to tell you what the group operation is, and I just use the ordinary addition, which of course makes R into an abelian group. And on G, well, we have some blob, and the blob is smooth and so on. Okay, is a Lie group homomorphism. That is, so I should say, that is a smooth map Xi for which we had this before, but it doesn't harm writing this down again. What does Lie group homomorphism mean? It means you can first take elements in here and compose them. So in this case, it's say two parameters, two real numbers. And how do you compose them? Well, lambda 1 plus lambda 2, that's the group law. But you could have equally well, and that's the group homomorphism part, could have equally well mapped first one of them and then the other one, and then blobbed the result using the group operation there. That's a group homomorphism. And any such thing is called a one-parameter subgroup. So if you want, it's the embedding of a one-parameter group into the big group. Okay? So then we have a theorem which one could prove. It comes again in two parts. And the first part is that Xi A from R to G, where Xi A of lambda is defined as exp of lambda A, is a one-parameter subgroup, is a one-parameter subgroup of G for any choice A in the Lie algebra. Okay? So if I now take an A and then I scale it, you have a one-parameter subgroup. If you think back of the circle, right? So one-parameter subgroup you have there. So that's one thing one can show. It's not so spectacular. One already, because you see, in particular, if lambda is 0, you have exp of 0. You can think about it. Exp of 0 yields you the identity. Okay, so you always go through the identity. So the points you cover, so Xi A of all of R is a subset of G, contains the identity, and indeed you also always have the inverse element, because obviously the inverse element of Xi A of lambda is Xi A of minus lambda. So let's say here in particular, you take the Xi A of some lambda, and that's a group element. Now, the A is not an index, it's just a chosen tangent space element. And you can ask, if it's in the group, what is its inverse? And so what is its inverse? And the answer is that is Xi A of minus lambda. Okay, and the second statement is any one-parameter subgroup, or one could also call it any one-dimensional subgroup of G, is of this form. Okay. So the Lie algebra allows us to understand all the one-parameter subgroups of our Lie group. Questions here? Okay. So then we conclude with a theorem. It's one of the theorems like one would expect it. So let's say you have two Lie groups, G and H, and you have a smooth map from G to H, which is a group homomorphism. So F, so smooth, and well, F of G1, the blob in G, G2 is required to be F of G1, blob in H, F of G2, right? If you have this, that's a group homomorphism. Then the following diagram, G goes here, F. You can actually go up here from the Lie algebra by an exp. You can go up here by an exp, TEH. And if you have a group homomorphism from G to H, you can check that the push forward that's associated with it really takes you from TEG to TEH, and that is because a particular implication of having a group homomorphism is that F takes the identity and maps it to the identity. So the identity in G is being mapped to the identity in H. That follows from the group homomorphism property here. That's not difficult to show. And so indeed, the push forward of a Lie group homomorphism really maps you from one Lie algebra into the other guy. And then the statement of the theorem is that this diagram commutes. And we know what that means. It means you can go either way. You can either go from here to here, or you can go this way. So that is, let's spell it out nevertheless for practice. That is that F of exp of A, so an A therefore is an element of TEG, is the same as exp of the push forward of the same A. So you can exchange this. And this is convenient, right? That you can use that the exponential map, in a sense, commutes with Lie group homomorphisms, but of course, if it jumps in there, it needs to become the push forward associated with that Lie group homomorphism. That's it. Okay, so at this point, all that remains is to solve some problems on an upcoming problem sheet over Christmas. But that finishes our formal discussion of Lie groups and Lie algebras.